All right, today we are diving into some really cool research about a new method for training AI that is, well, it's incredibly simple, but shockingly powerful. It's called dynamic fine-tuning, or DFT for short. And honestly, it might just flip the script on how we think about making AI smarter. So let's just jump right in with a question that gets to the heart of a huge headache in the AI world.
Think about this for a second. What if the most common, the go-to, the default way we have of training an AI for a new job, what if sometimes it actually makes the AI worse at it? I know it sounds completely backwards, right? But it's a very real problem, and it perfectly sets the stage for the big idea we're talking about today. So yeah, this whole issue is what researchers have dubbed the fine-tuning dilemma. It really comes down to a fundamental trade-off between the two main ways we teach an AI to do something new.
Okay, so on one side, you've got the most popular method by a long shot, Supervised Fine-Tuning, or SFT. The idea here is super straightforward. You take a big, powerful base model, and you just show it a ton of high-quality examples from human experts, showing it exactly what you want it to do. It's the standard for a reason. It's pretty easy to set up, and it's fast at getting an AI to copy what it sees.
And here is where that dilemma kicks in. You've got SFT, which is simple, it's fast, but its big weakness is that it tends to just memorize the answers you feed it. It's a classic problem called overfitting. Then you've got the other option, reinforcement learning, or RL. Now RL is way more powerful. It learns to generalize from trial and error, which makes it way more flexible and robust. The catch? Oh, it's a big one. It is incredibly complex, it's slow, and it is super expensive to run. And look, this isn't just some abstract idea. It's a really well-known problem in the field. The researchers in this paper sum it up perfectly. SFT memorizes while RL generalizes. Models trained with SFT they often fall apart when they see something new, something that wasn't in their training flashcards. So the billion-dollar question is, why? Why does this happen?
Answering that why is really the secret sauce of this entire research paper. It turns out SFT has this kind of secret identity, and once you see it, you understand exactly why it has such a hard time generalizing.
So here's the breakthrough. By looking at SFT through the lens of reinforcement learning, the researchers found something huge. SFT isn't a totally different thing. It's actually a very specific, special version of RL. But, and this is the key, it's a version of RL that's running with a fundamentally broken, totally unstable reward system. That is the root cause of all these problems.
Okay, let's break this down. Picture SFT as a game. Every time the AI gives an answer that perfectly matches the expert's answer, it gets a reward. Simple enough. But here's the flaw the researchers uncovered. The size of that reward is inversely proportional to the model's own confidence. So think about that. If the model's totally unsure, basically makes a wild guess, and happens to get it right by pure luck, it gets a massive, system-destabilizing reward. This encourages the AI to chase these lottery ticket wins, which causes it to overfit on weird little patterns in the data, instead of, actually learning the core concepts.
So the reward system is broken. The game is rigged. How in the world do you fix it? Well, the solution these researchers came up with is just beautiful. It's so elegant. It's called dynamic fine-tuning, or DFT.
And you want to know the best part? The fix is a single line of code. That's it. No needing more data, no begging for bigger models, no re-architecting the whole thing, just one simple, elegant tweak to the math. So how does this one line of code work its magic? Well, from a high level, what DFT does is it dynamically adjusts the training goal based on how confident the model is about each specific word, or token. This little tweak completely neutralizes that wacky inverted reward system we were talking about. So instead of giving these giant payouts for lucky guesses, it creates a stable, predictable, uniform reward for every single correct token. It, quite literally, fixes the game.
Okay, a one-line fix that changes everything. It sounds amazing, maybe a little too good to be true. But does it actually hold up in the real world? Well, the researchers put DFT to the test, and the results they're pretty jaw-dropping.
Just take a look at this table. It's showing the performance boost over the original base model on some tough math reasoning tasks. For that first model, Quen, the standard SFT method gives it a little 2-point bump. Not bad, but DFT, it gets a nearly 16-point gain. That is almost 6 times better. And you see the same story again and again across different models. The improvement isn't just a little better, it's a whole different league. But this This, to me, is the craziest result of all. On a super hard benchmark of Math Olympiad problems, standard SFT didn't just fail to help, it actually made the model worse. Its accuracy went down because it just memorized patterns and forgot how to reason. DFT, on the other hand, a massive 11-point gain. This is crystal clear proof. DFT shines exactly where SFT falls on its face, showing it can generalize so much better.
But the benefits don't stop there. It's not just about getting a better final score. It turns out that DFT is also a ridiculously efficient learner.
Look at this number, 20. Just 20. That is how many training steps it took for DFT to get a better result than SFT could ever achieve even after hundreds and hundreds of steps. I mean, that's just incredible efficiency. That fixed reward signal isn't just better. It's cleaner, it's more direct, and it guides the model to the right answer with so much less wasted effort.
Okay, so we've established the DFT works better and it works faster. But the really deep question is, why? The final piece of this puzzle zooms out to explain the learning mechanism itself, and it shows a fundamental shift in strategy.
This visual basically tells the whole story. It shows two completely different ways of learning. SFT's approach is to become slightly more confident in everything. It just kind of nudges up the probabilities on all the words in the right answer. But look at DFT. It is so much more strategic. Its approach is to become very confident in what matters. It creates this polarizing effect where it jacks up the confidence on the really important words while actively pushing down the others.
So what does that actually mean? It means DFT learns to focus its attention. It zeroes in on the key high-value tokens, the words that actually carry the meaning. And at the same time, it learns to ignore or suppress the common low-value stuff. Words like the, let, or just commas and periods. This forces the model to build a much deeper, more robust understanding of what it's learning.
Here's the best analogy. SFT is like trying to learn for a test by memorizing every single word in the textbook, including all the ands and buts. DFT, on the other hand, is like highlighting and focusing only on the key concepts, the definitions and the formulas, the stuff that actually matters for understanding the subject. It is just a fundamentally smarter way to learn.
Which kind of leaves us with this one last big, thought-provoking question. We're in this race right now, obsessed with building bigger and bigger models, throwing more and more data and computing power at them. But what if the next real breakthroughs don't come from more brute force? What if they come from more elegant, more principled fixes like this one? What if truly understanding how these things learn is the real key to unlocking what they can do? It's definitely something to think about. Thanks for tuning in.